This video is part of the lecture for multivariable calculus, and I'm going to talk about velocity and acceleration. Let me start by saying that r of t is the position vector of a moving object. Then if we take derivative of r of t, then there are some usage for that. Usage of r prime of t. The first one is to find the tangent line. So finding tangent line to the parametric curve r of t. Since r prime is tangent to the curve r of t, then we can say that we can use r prime to find the tangent line, and actually the direction vector of the tangent line would be r prime of t. Then the second usage of that we are going to talk today would be finding velocity and acceleration. Finding velocity and acceleration. So velocity is actually a vector. So assume that we have the position vector r of t. At the time t, we are here, and at the time t plus 1, t plus delta t, we are here. And let's assume that I have the origin. I'm going to make a vector from the origin to r of t, and I'm going to make another vector from the origin to r of t plus t. And then, as you know, the velocity would be the change in the position over time. So r of t plus delta t minus r of t, which would be this vector in here, divided by delta t, would be the velocity as delta t goes to 0. So I'm gonna say that v of t, so velocity vector v of t is actually delta r over delta t, and when we take the limit of that as delta t goes to 0, and we show it by dr over dt, which is basically, if you have the component of r, then we're gonna take derivative of each of the component with respect to t, actually. dx dt, dy dt, and then dz dt. That's the velocity vector. But you notice that velocity is a vector, so it has a length and it has a direction. So the velocity vector has a length, and the length of the velocity vector is actually very famous, and it's called speed. So notice that speed is the length of a vector, therefore it's a number, it's a scalar. But the velocity itself, it's a vector, so it has a direction. So the direction is also important, and the direction of the velocity vector is tangent to the curve, position curve. Why? Since when delta t goes to 0, r of t and r of t plus delta t would be very close to each other. So as delta t goes to 0, we can get this vector in here as delta r, and then this vector in here, and as you see, that we can get tangent to the curve. Okay, so that's the velocity, which is dr over dt. And in particular, something that is important in the problems, in particular, the unit vector is the velocity vector over its length, and we show it by t. Okay, there is also acceleration vector that is important. So acceleration vector, and we're gonna show it by a of t, which is basically derivative of the velocity vector. So if we have the velocity and we take derivative of that, we get acceleration. And therefore, we can say that it's the second derivative of the position vector. Okay, so we take derivative of, so we take derivative, the second derivative of each of the components. So d squared y of dt squared and d squared z dt squared. We take derivative of each of the components twice, and in that case we get the acceleration vector. So a of t, the acceleration vector, is dr, the second derivative, dt squared. Okay, so that's about acceleration and velocity. Let's look at one example. So example, let r of t to be cosine of kt, sine of kt, and 0, where k is a constant. K is just a number. Then what is the velocity? Velocity, v of t, is actually derivative of the position vector. Let me move this one a little bit. And now take derivative of cosine of kt. So k is just a number. Derivative of inside, which would be k. And then derivative of cosine would be negative sine of kt. Sine of kt derivative would be k. Cosine of kt, derivative of 0 is 0. How about acceleration? So acceleration, we show it by a of t, which is the r double prime of t. Now k is just a constant. I'm gonna write negative k, and then derivative of sine of kt using chain rule, it would be k cosine of kt, and the derivative of k cosine of kt would be k squared negative sine of kt, and then 0. Okay, look at r of t. Actually, it is x, this is the y component, this is the z component. As you know, cosine squared plus sine squared of anything would be equal to 1. So I have x squared plus y squared equals to 1. So I have a circle in here, circle of radius 1. Let me graph it. X-axis, y-axis, and I have a circle of radius 1. This is my r of t. Okay, this is the circle of radius 1. And assume that I'm here at the time t, I'm at this very specific point. When I take derivative of that, I get this vector in here, and you may notice that rt dot product with r prime of t would be equal to 0. Why? It's just because I get cosine of kt times sine of kt with a negative k, plus I have sine kt, cosine of kt plus k. So I have a negative k, and then I here positive k, so everything together would be cancelled. I get a 0, which means that r of t and r prime of t would be perpendicular to each other. And so this would be r prime of t. So you see, it is, if from the origin at the time t, this is r of t, then r prime of t would be exactly like this vector. And the length of r prime of t would be actually this speed, and it's equal to the first component square plus the second component square, and I get a k. And about acceleration is, if you see, you can multiply, you can find the dot product of r prime and r double prime, and then you will see that the dot product of these two is also equal to 0, and acceleration, actually with the negative k that we have in here, acceleration is this vector toward the origin. This is the acceleration, r double prime of t. And r double prime of t is actually the length of the acceleration, and it's equal to k squared. Okay,